Welcome back to the deep dive. If you've spent any time programming, you know the comfort zone. You've got your integers, your floats, a string for a name.
Right, the simple, clean variables.
Exactly. But let's be honest, the real world, it rarely fits into those tidy single-value boxes.
It never does.
Yeah.
And that's really the fundamental disconnect, when you move from exercises to building real systems, whether you're making a simulation or tracking inventory or whatever. The data you need isn't just a list of integers. It's a complicated mess. It's heterogeneous.
Absolutely. We've been diving into foundational material on data structures, and the mission today is to give you the tool that bridges that exact gap. We need to get beyond simple, homogeneous collections.
Where every single item has to be the same data type.
Right. And get to a point where we can build our own custom data records.
That's it. Our focus is on compound and heterogeneous types. I mean, think of it this way. We aren't just storing data anymore. We're modeling reality. We need a way to create a completely new custom data template. A single container that can blend, say, an integer, a string, and a float, and treat them all as one coherent thing.
Okay, let's unpack this then. Our mission is to understand how to efficiently represent these complex records, student files, inventory, geometric coordinates, you name it, by bundling different data types together using the C++ struct construct. So let's start there with that core concept. The difference between homogeneous and heterogeneous.
Sure.
We're all used to basic types, int, float, and compound types like arrays, vectors, strings. What's the common thread there?
They are, and this is the key word, homogeneous. They're collections, sure, but every single element in that collection has to share the exact same type. An array of integers can only hold integers.
And a vector of strings only holds strings, which is great for, a list of temperatures or something.
Exactly. It's perfect for repetitive data. But the second you try to model something more complicated, that homogeneity becomes a huge limitation.
The language itself can't possibly have a predefined type for every real-world thing we might want to represent.
No way. And the student record example from the source material is perfect for this. It's so clear.
What does that look like?
Well, a single student record isn't homogeneous at all. It needs an integer for the ID, a couple of strings for the name and address, and then, a float for the GPA.
You can't put all that into a single array.
You can't. If you tried, you'd end up with, 3 or 4 separate arrays?
Yeah.
One for IDs, one for names, one for GPAs.
And you just have to trust that the data at index 5 in the ID array corresponds to the data at index 5 in the name array.
Which just screams instability. It's asking for trouble. You need a way to enforce that coherence. You need a custom package, a structure, that defines what a single student is. And this is why we turn to the struct construct in C++ Ren. It lets you, the programmer, create that exact heterogeneous record.
And what's really interesting is that struct is so foundational to the language that you don't even need to include a special library.
Nope. No headers, nothing. It's just built right in.
It's a true building block.
It is. Now, we should probably mention its close cousin, the class. That's a bigger topic, usually for object-oriented programming.
Right.
But for creating these simple, custom data records, the struct is the perfect place to start.
Okay, so let's move into actually building one. If I decide I need a custom type, let's call it a student, what am I really doing when I write that struct definition?
You are creating a blueprint. A structure is a user-defined, compound, and typically heterogeneous type.
The key word there is type.
Exactly. When you write struct student, you haven't stored any data at all. You've just created the template for what a student will look like in memory.
A great simple example is a 2D point on a graph. A point is two numbers, x and y, but you need the program to treat them as one single thing.
Right, one indivisible object. So we define a point structure with two members, x and y. Once that blueprint is set, we move on to instantiation.
Which is making an actual usable object from our new type. And this is where the memory actually gets allocated. So walk us through that. It seems like declaring a simple variable, but there's more going on under the hood.
A lot more. When you declare, say, point P1, the system allocates enough memory, all in one block, to hold both the x-coordinate and the y-coordinate, and it bundles them under that single name P1.
And these standard objects, they typically go into the stack memory segment, right?
They do.
For our listeners who might not be deep into memory architecture, why does it matter if an object is on the stack?
Speed. Stack objects are fast. Very, very fast. Memory allocation and deallocation is all automatic. They're perfect for temporary use inside a function, but they have a short lifespan. They vanish when the function ends.
But often you have data that needs to live longer than that, or you have so much data that the stack can't handle it.
Correct. And that's when you need dynamic objects, which are allocated in the heap memory segment.
The heap is slower.
Much slower, but way more flexible. If you need 1 million student records, you're putting them on the heap. You use syntax that looks like declaring dynamic variables, and you almost always need a pointer to manage that memory location.
That's a really clear distinction. Short-lived speed versus long-lived flexibility. Okay, so we've instantiated our P1 object on the stack. How do we get to the X or Y values inside it?
We use member access. The individual variables inside the structure, the members, they act like normal variables, but you have to go through the object's instance name to get to them.
And this is where the syntax gets really specific. There are two main ways to do it, depending on if you have a direct object or a pointer. For a direct stack-based object like our P1.
You use the dot. The dot member access operator, you just write the object name, then a dot, then the member name. So P1.x is L10. It's clean, simple, direct.
But if you're working with a pointer, say if you allocated it dynamically on the heap, the syntax is totally different.
Then you use the arrow pointer operator. If you have a pointer, say PPTR, that points to your structure, you'd access the member with PPTRX.
And you said that's a shortcut.
It is, yeah. It's basically a shortcut for 2 steps.
Yeah.
First, go to where the structure is in memory, and then find the specific member inside it.
So what's the long version? If the arrow is a shortcut, what is it shortcutting?
Good question. The alternative is to explicitly dereference the pointer first. That momentarily treats the pointer as the object itself, and then you can use the dot operator, so it look like ptr.x.
Oh, the parentheses are critical there.
Absolutely, because of operator precedence. The arrow operator is just so much cleaner and easier to read.
That level of detail is really what separates someone just using structs from someone who understands how they actually work.
Okay, but let's talk flexibility. Defining a struct with fixed types, like only int for x and y, feels really limiting.
It is. It absolutely is. And that leads us right into template structures. If we only defined our point with integers, the moment we need fractions for, I don't know, a physics simulation, we'd be stuck.
You'd have to write a whole new structure, right? Like float point or something. It's exactly a new struct that looks identical to the first one, but just uses float members instead.
You're repeating code just because of a type of difference. The blueprint is the same, but the materials are different.
You got it. And the solution is to make the structure generic by using template types. Templates are basically placeholders for a type that you, the programmer, will fill in later when you create the object. It's all about code reuse.
So one single definition can meet all your type requirements. How do we define that?
The syntax is a lot like function templates. Before the struct definition, you add a template declaration. Template class T1, class T2.
T for type, I'm guessing.
Traditionally, yeah. And you can have as many as you need if the members have different types.
That's incredible flexibility. The sources use a templated rectangle, which makes sense. The length and width could be integers or floats or doubles, depending on what you're doing.
And here's the key part for anyone learning this. The instantiation syntax is different. Since the definition is generic, you have to tell the compiler which types to use when you declare your object.
You're filling in the blanks you left in the template.
Yes, exactly. You pass the actual types in angle brackets after the struct name.
Yeah.
So for our generic point, if you wanted integers, you'd write point float P1. If you wanted floats, you'd write point float P2.
And the compiler just swaps in int or float for T and generates the right code.
That's all it is. It's a really powerful way to write adaptable code.
It is. Okay, so now that we can define and instantiate these custom objects, let's shift gears and talk about operational rules and efficiency. What can we actually do with an entire struct automatically?
That's the perfect question because it reveals the struct's limitations. What works out of the box? The answer is surprisingly little.
So we can't just treat our new custom type like an int. What's the one big exception?
The single exception is aggregate copy, the assignment operator. You can copy one struct object into another, and it works member by member automatically.
So if I have student A and student B, I can just say student A and student B.
Yep, and the compiler will copy the ID, the name, the GPA, everything from B to A. It's very convenient.
Okay, that's the good news. Now the limitations. What can't we do?
Pretty much everything else. You can't use the standard input or output streams on the whole object. You can't just do send student A.
The program wouldn't know how to parse the input for your custom format. That makes sense.
Right, and you also can't use standard comparison operators. You can't check as student A equals student B.
On what basis would it even make that comparison? The ID. The name, all 10 members.
Exactly. Since the compiler doesn't know the criteria, it just refuses to guess.
So to output a student record, or compare two of them, I have to go member by member.
That's the default behavior. Now, for anyone curious, you can teach the compiler how to do these things by overloading the operators, but
But that's a much bigger topic for another day.
it is usually covered in object-oriented programming.
Got it. Let's talk efficiency, because this is where design choices really matter. You pass structs to functions all the time. You can pass by value, which is the default, or by reference. Why is passing by value generally a bad idea for structs?
This is a huge efficiency warning. If you pass a struct by value, the program has to make a complete copy of the entire thing.
Every single member.
Every member. Imagine our student struct. It might have large strings, numbers. Copying all of that data takes memory and, more importantly, time. Every single time you call that function.
It seems incredibly wasteful, especially if the function only needs to read, say, the student's ID.
It is, which is why the recommended practice is almost always a pass by reference. When you do that, no copy is made. Yeah, the function just gets a memory address, a direct link to the original data. It's so much faster.
So always pass by reference if you can. Does that same logic apply when a function returns a struct?
It does, yes. Returning a struct by value has the same cost. It has to copy the entire thing back to where it was called. If you can, it's often more efficient to pass the struct in by reference and have the function modify it, rather than returning a new one.
Okay, before we wrap up, let's touch on two advanced uses that really show how structs fit into a larger system. First, what if I need to store a lot of them?
Well, once you've defined your student struct, that name, student, becomes a brand new valid type in your program.
So you can use it like you'd use int or string.
Exactly. If you need to store 20 students, the natural choice is a vector of students. You just declare a vector student class roster. It's that simple.
And the second one, which is more about code organization, is the nested struct.
This is such a great organizational tool. Think back to our student. It probably have first name, middle initial, last name. If you see that same group of members in a teacher struct and a parent contact struct, that's a signal. You should probably make a dedicated name struct and then use that name struct as a member inside your other bigger struct.
So instead of 3 string members for a name, you just have one member, name student name.
Right, and it makes the code cleaner, easier to read, and way more logical. You're applying abstraction to your data design.
Okay, let's tie this all together for you, the learner. We started with the limits of simple variables and homogeneous arrays, which is really just data storage.
And we showed that structures provide the essential tool for data modeling. They let you represent that complex, mixed-type, heterogeneous data. And you absolutely need that to model anything from the real world.
Knowing the structure of your data is everything. It determines how you read it, parse it, store it. Getting this right gives your whole program a strong, coherent backbone.
And that foundation is what lets you build robust, scalable apps. You now know how to design the blueprint for any complex object, define its generic requirements, allocate memory for it, and access its parts efficiently.
Structures truly allow us to perfectly model complex real-world objects. We've seen examples from geometry to student records, but here's our final thought for you to think about, something that pushes this beyond math or databases. If structures let you design a totally custom data contract, what unexpected, non-traditional objects could you model? Think about designing a struct for a telemetry packet from a deep-sea drone. Every sensor, reading temperature, pressure, battery level, depth, all organized with a specific type and structure. That custom contract enables instantaneous, error-free parsing. So, what custom contract does your next project need?